Okay, so let's begin. We are going to discuss some special types of graphs, special classes of graphs. It's not just a small type, whole classes of graphs with many applications that you see them a lot, especially trees and bipartite graphs, and then next time we'll talk about planar graphs. Okay, so these are important graphs and very specific in their structures. They have, and so we study their structure separately and then exploit them for applications. Okay, as we develop a whole theory for these things, and they're fundamentally different than the journal graphs, right? So the specific structures to them is very important, and this is what you will encounter a lot in your data structures course. Today, trees is one of the words you will hear the most in your data structures course. Is the tree based data structure or hierarchical data structures. Okay. So before that, I just want to give you a few, just utter a few names of some classes or types of graphs. So you hear the name and but understand them. There is no deep concept, just a definition, some examples, and maybe a quick question about that, so that you understand these things. And when you see it later, you should have this in your vocabulary at your fingertips, so you understand it quickly. So the first type of graph, first class of graph that we see, and you will hear these words, is the complete graph. Okay, a complete graph is a simple undirected graph. Generally, we are going to speak about simple undirected graph today. So it's a graph on certain number of vertices, such that every vertex is adjacent to every other vertex, right? So all possible edges that could be present in the graph are actually present in the graph. Okay. Is this clear? So if you look at how would its adjacency matrix of a complete graph look like? Complete simple undirected graph. So the matrix will be full of ones, because I said every vertex is adjacent to every other vertex. What will be the degree of a vertex? What will be the degree of any vertex? All vertices will have degree n minus 1, right? So these are some examples of K1, we typically denote them by Kn, because when the number of vertices is given, the graph is fully described. We know exactly the number of edges and who is adjacent to whom. So the number of edges, the set of edges don't need to be specified, right? We just give the number of vertices. So it's typically denoted by Kn, K sub n. So complete graph on n vertices. So here is a complete graph on one vertex, right? All possible pairs of vertices are adjacent in K1. There is no edge there. It's an empty graph. K2 is just an edge, two vertices, all possible pairs. There is only one pair, and that's an edge, right? K3 is this, generally we call it a triangle, right? Is K3 is a three vertices all adjacent. Okay, K4 is a complete graph on 4 vertices, K5 a complete graph on 5 vertices, and so on, right? You can just make now you see what's the degree of this vertex? In K5 the degree of every vertex will be 5 minus 1, right? In K3 the degree of every vertex will be 2 or 3 minus 1, okay? 3 minus 1, 2. So how many edges are there in a Kn? Generally, in terms of n, what is the number of edges? N minus 1. How many edges are there in Kn? Sorry? Why n choose 2? Why n choose 2? You said n choose 2? Why? The number is not important. Why then choose 2? Why n times n minus 1?
It's because like there are n vertices and every n has n minus 1 edges.
Sir, n नहीं होना चाहिए.
N?
Yeah.
Okay. Let's see. Does this have 5 edges? Yes.
The number of edges is the number of two subsets that can be made from the vertices, so that's the maximum possible n.
Is n choose 2, right? So look at the definition. All possible edges are present, right? What are possible edges? Pair. A pair is a possible edge, right? How many pairs can be made from n vertices? N choose 2, right? That's one way to do it. I told you a complete graph, the adjacency matrix will be full of ones except for diagonals, right? So how many ones are there in a complete graph? In the complete graph adjacency matrix, how many ones are there? N squared. Yes, so you look at every row has n minus 1 ones, right? Diagonal is 0, the rest are ones. So every row has exactly n minus 1 1. So that is n into n minus 1. But that every edge is counted twice, right? Once in upper triangular matrix and once the lower triangular matrix. If AB is an edge, then there is a 1 in the row of A and then there is a 1 in the row of B also, right? So we need to divide it n into n minus 1 by 2, right? Or by the handshaking lemma, n into n minus 1 is the sum of the degrees, right? You add up all the degrees. The degree of first vertex is n minus 1, that of the second is n minus 1, the third one has n minus 1 adjacent vertices. If you add them all up, you'll get n into n minus 1. But that's sum of the degrees. Sum of the degree is always equal to twice the number of edges. So you half it, you'll get the number of edges. Okay? Many ways. So the answer is n choose 2, n into n minus 1 divided by 2. Okay? The path graph, denoted by Pn, P sub n, it's a path on n vertices, right? We know what a path is, a sequence of vertices such that every successive pair is actually an edge, right? So a path graph is actually the path. So the graph is nothing else but a path, right? It's a path on n vertices, is denoted by P sub n. What is the degree in a path? What is the degree of the first vertex? Who is the first vertex adjacent to? It's a sequence of vertices. Every successive pair is an edge. Who is the first vertex adjacent to in this sequence? Only the second one. What's the degree? What's the degree of the second vertex? Or who is the second vertex adjacent to? The second vertex, the third vertex, first vertex, right? So it has degree 2. What's the degree of the kth vertex? Any internal vertex has degree 2. Once the next one and once the successor and predecessor, right? The next one and the previous one. And the last vertex is only adjacent to the previous one, right? There is nothing, it's last, there is nothing there. So in a path graph, every vertex, so a path is a sequence of vertices, every vertex has degree 2 except for the first vertex in the sequence and the last vertex in the sequence, right? It's a path, no repetition, simple walk, right? Here are some examples of paths. It's a path on 4 vertices. 4 vertices, you can write them in this order or draw it in this order. So the first vertex has degree 1, the last vertex is degree 1, and the middle 2 vertices have degree 2, right? The internal vertices, these are called the internal vertices, and those are called the end vertices or endpoints. Okay, just like endpoints of edges. Is this clear? Path vertices? Yes? How many edges would be there in a path vertex on n vertices? A path graph on n vertices. Again, how many edges in a graph is there? Sum of the degrees divided by 2, right? What is sum of the degrees of the path vertex? Or how does the matrix, how does the adjacency matrix of a path graph look like? So let's say the first vertex is V1, it's the first row. The second vertex is V2, that's the second row, then the third row, then the fourth row, right? So this path graph, suppose vertices are ordered, rows are ordered in this order, right? So the first row, second row, third row, fourth row. How would the matrix look like? How many ones will be there in the row corresponding to this vertex? the first vertex or in the first row? How many? How many ones will be there in the row corresponding to the first vertex? 1. How many rows will be there in the rows corresponding to the second vertex? How many ones will be there? 2, right? So, if I order them, the first vertex is the first row, the second vertex is the second row, and so on. So, the first vertex will have the second index 1, right? The second row will have the first and the third index 1, right? So it will look like this. So the matrix will look like this. So V1 is adjacent to V2 and nothing else, right? V2 is adjacent to V1 and V3, right? V3 is adjacent to V2 and V4. V5 is adjacent to V4. Does it make sense? So it will be just this 1, 1, 1, 1 like this in the diagonal, close to diagonal. This will be the only one, and here it will be like this, the last one. Okay. So what will be? How many edges are there in a Pn? How many edges will be there in Pn? Why? Each edge corresponds to 2 vertices. Doesn't make how many edges will be there in a path on 5 vertices? How? Why 4? No, you said 4. I heard that, but I need.
Sir, n minus 2 edges will have 2 vertices.
N minus 2 vertices will have degree 2. Yes.
So 2 se multiply kar denge and then.
Okay, so she says that n minus 2 vertices will have degree 2. So the sum of the degrees of these n minus 2 vertices is 2 times n minus 2. Then
to prevent double counting, we divide it by 2.
there is no prevention. There is no, you didn't even count the sum of the degrees. Okay, so I think she wants you to use the handshaking lemma, which says the sum of the degrees is equal to twice the number of edges, right? So I don't know how to find the number of edges. Let's do sum of the degrees. So sum of the degrees is n minus 2 vertices. The middle internal vertices have degree 2, all of them, n minus 2 of them have degree 2. So if I was adding up all the degrees, the sum of the degrees will be 2 times n minus 2 plus 1 for the first endpoint, 1 for the last endpoint, and that will be 2 times n minus 2 plus 2, right? So that is equal to 2 times n minus 1. That's the sum of the degrees, 2 times n minus 1. The number of edges by the handshaking lemma is half of that, and that is n minus 1. Okay, and earlier also we said that the path has exactly n minus 1 edges, right? There is a, so if there are 5 vertices, there is an edge between every pair, and the number of these pairs, successive pair, is n minus 1. Okay, so the number of edges will be n minus 1. Okay. Cycle graph is just like we know cycle. So it's just like a path graph, but the first vertex, the so-called first vertex, is now adjacent to the last vertex. So first and last are just meaningless statements now. They lose their meaning because now they are no more first, they are like cycles. So the degree of every vertex in a cycle is equal to 2, right? So here is an example of C6. It has 6 vertices. Every vertex is adjacent to the previous one and the next one. If you can identify, or let's say every vertex is adjacent to one vertex, the next one counterclockwise, and the next vertex clockwise. Okay, so in both orientation to the previous and the next, however you define it. So the degree of every vertex is 2. You know, it's a cycle. Why do we call it a cycle, right? It's a sequence of vertices. Every successive pair is an edge, and the first vertex is the same as the last vertex, right? A sequence is a linear thing. A cycle is just this 2D thing. Okay, so how many edges will be there in a cycle on n vertices? Why n? Sorry?
Every edge is connected.
Every? No. What is every two vertices? This vertex connected to this vertex by an edge? So every two vertices are adjacent? Every adjacent vertex is adjacent. That's a good one. Yeah. So every vertex has degree 2, right? It's written on the board, right? Is this clear? So if I add up the degrees, adding up, summing up, sum of edges is not a thing, okay? Sum of vertices is not a thing. Sum is applies to numbers, right? So sum of these degrees is equal to 2 times n, if n is the number of vertices, right? Now by the hand checking lemma, the number of edges is half, so half of sum of the degrees. The sum of the degree is 2n, divide by 2, you will get the number of edges, okay? So length of in the cycle vertices there will be exactly n edges, okay, in any cycle on n vertices, and you can verify it here. This is a cycle on 5 vertices. How many edges are here? 5. This is a cycle on 3 vertices. How many edges are there? 3, right? A cycle on 6 vertices, we have 6 edges, right? So makes sense, okay? Okay, so the number of vertices in a cycle graph is n, okay? In Cn is n. Okay, the next one is the wheel graph. Okay, we call it the wheel graph. It's not a standard word, but it's a cool thing. Sometime it appears, you will see them. Cycles, paths, complete graph, very much, you will see this any serious graph theory, any serious social network analysis, any serious internet work will talk about those things, right? These are not just words. I just want to do it for the sake of completion, and these are funny, good diagrams, and they don't take too much time. Now, wheel graph is a cycle plus another vertex which is adjacent to every other vertex. Okay, so it's a cycle, then this is what we call the center or the hub of a vertex, and this is now adjacent to every other vertex. Okay, so the cycle, every vertex has degree 2. Now in a wheel, every vertex, those outer vertices have degree 3, because 2 is for the cycle one and 1 is to this hub, right? And what is the degree of the hub? If the wheel is n plus 1 vertices, what is the degree of the center vertex? N, right? So it's not adjacent to itself, it's adjacent to every other. What's the degree of the other n vertices? What is the degree of any of the other n vertices? 3, right? 2 was in the cycle and 1 is now the center. Yes? Go ahead. Sure. No, there are n plus 1 vertices. Na? When I say Wn, there are n plus 1 vertices, just to make it easier. Okay, Wn means n plus 1 vertices, right? Unless you define it differently, we're not going to perhaps see it again in this course. But if you want to, if you mean that Wn has n vertices, then the middle one will have degree n minus 1, and the cycle one till will have degree 3, but there will be n minus 1 vertices there, right? So what is the number of edges in a Wn? Just do sum of degrees. If you can do counting, basic from the diagram. What is sum of the degrees? Don't answer. Now, what is sum of the degrees? Cannot be 3n is just for the outer vertices, not counting the inner vertex, right? What is the sum of degrees? 3n for the border vertices, right? Or the fence vertices, and there is, what is the degree of the center vertex? N. So that was 3n and this is 4n, right? So this n is 4, total sum of degrees. So what is the number of edges? 2n, right? And you can verify it. You can see there will be 1, 2, 3, 4, 5, 6 plus 6, 12 vertices in W6. Is this clear? So this was just to give you practice of the names and cycles and paths and to understand the thing. One more or two more. So there is a cycle. We saw it, right? Just a fence. Then there is a wheel, which is plus cycle plus the center. If you just look at the center vertex and those edges that are adjacent to the center, incident on the center, this is called the star graph, right? Just as the name suggests, there is a star graph on n vertices, has one vertex whose degree is n minus 1, and all other vertices have degree exactly 1. Okay, so it's one center vertex. Look at this thing, one center vertex, 5 vertices, one vertex whose degree n minus 1, 5 minus 1, and all other vertices, these are called the leaves or these tendrils or these branches, these have degrees n 1, right? Everywhere. Is this clear? Yes, cycle graph, a star graph. So now if you look at the star graph and superimpose on top of it, insert on top of it, enclose it in a cycle, you will get a wheel graph, right? Yes, please.
Can you go to the last slide? Like if you do W4, it has 5 vertices but 8 edges.
W4, it has 5 vertices. Yeah, so W4 has 2 times 4 edges. No? Okay, so the cycle was says star graph.
So how is S2 a star graph? Because in that both of them are the same.
So that's a good question. How is S2 a star, right? You define it. I said there is one vertex which is adjacent to all other vertices, and all other vertices have degree equal to 1. So I can think of this as a star, and this is adjacent to all other vertices, and these are all other vertices who have degree equal to 1. Right? So it's your choice. If your notation doesn't go good with it, you can define this to be a star is defined on at least 3 vertices, right, or something like that. Is this clear? So how many vertices edges will be there in Sn? N minus 1. Why?
Because n vertices, the center one is adjacent to all the vertices. The center one has the number of edges n minus 1.
N minus 1 plus n minus 1 divided by 2.
Yes, n minus 1 plus n minus 1. What is that?
So apart from all,
What is n minus 1 plus n minus 1? Like not the value. What
the
is?
first n minus 1 is from excluding the central. All others are connected with exactly one.
Adjacent. But not what are you doing when you say n plus 1? What does n minus 1 plus n minus 1 represent?
Sum of the
Is the sum of the degrees, right? So you add up the degrees. The middle vertex, the central vertex has degree n minus 1. The leaves or the other side vertices have degree 1. So 1 into n minus 1 plus n minus 1. So it's 2 into n minus 1 divided by 2, which is equal to n minus 1. Okay. Last one is hypercube, n dimensional hypercube. This is needed when you do parallel computing and those things. You encounter this, and it's always used a lot in error correcting code or coding theory, information theory. It's deep into communications, in signal processing, and also in parallel computing, parallel processing. It's a common topology for parallel networks, parallel computers. Qn is a graph on 2 to the n vertices. Okay, so for how many n bits length, how many n length bit strings are there? How many bit strings of length n? 2 to the n. So a Q sub n is a graph where there is a vertex corresponding to each unique bit string of length n. Okay. And now 2 bit strings are adjacent, or 2 nodes, 2 vertices are adjacent if the corresponding bit strings have exactly 1 bit different. Okay, this, you know the Hamming distance. You guys know Hamming distance? Hamming similarity.
Hamming loss.
Huh?
Hamming loss.
Hamming loss. Yeah, that's also related. You don't know Hamming distance? Didn't do any digital logic, digital circuits. This digital systems. Never heard of? Hamming distance of 2 bit string is the number of bits in which they differ. It's a proper distance metric. Okay, so you have a bit 0001 and you have 1001. What the Hamming distance between these two is 2, because they differ by the first bit and the last bit, right? 2 bits are different, otherwise they are the same. Okay, so the Hamming, so it's actually if 2 vertices have Hamming distance 1, if they only differ by 1 bit, then exactly 1 bit, then there is an edge between them. Okay, Q1 will have 2 to the 1 vertices, one corresponding to the bit string of length 1 and the other also corresponding to the other bit string of length 1, right? Is there an edge between them? Because what's the difference between this bit string and this bit string? How many bits are different in 1 and 0?
1.
Is 1 bit, so there is an edge, right? this Q2 will have 2 to the 2 vertices corresponding to 0, 0, 0, 1, 1, 0 and 1, 1, right? Two nodes will be adjacent if the corresponding bit strings have only exactly one bit different, right? So is 0, 0 adjacent to 1, 1? Is 0, 0 adjacent to 1, 1?
No.
Why not? Because they differ by the first bit and the second bit, right? But 0, 0 is adjacent to 0, 1 because they only differ the second bit, right? One bit different. 0, 0 is adjacent to 1, 0 because only differing by the first bit, right? So that's how hypergraph Q2 will be made. Q3 will have 2 to the 3 8 vertices corresponding to the 8 unique bit strings in a bit string. Now let's be give me, why is there an edge between 0, 0, 1 and 1, 0, 1?
It differs by 2 bits.
0, 0, 1 and which bits, how many bits are different between them?
The first and
Just the first bit, right? Why is 0, 0, 1 not adjacent to 1, 1, 0?
all the bits are different.
Yeah, there are 3 bits different, right? So they are not adjacent to each other, right? Is this clear? Yes? What is the degree of a vertex in Qn? What is the degree of a vertex in Qn? In Yn? Sorry? Yeah, so a vertex correspond to n bit string. Other strings that differ to this from this bit string by exactly 1 bit are exactly n. Though that string which is in which all is the same except for the first bit, that string in which everything is the same except for the second bit, right? So for each bit it could differ and give me another string, right? And that will be give me a neighbor or an adjacent vertex. Okay, so the degree of every vertex in Qn is n. Okay, how many vertices are there in Qn? 2 to the n. What is the sum of the degrees? 2 to the n times n, right? N times 2 to the n. How many edges will be there in Qn? Half of n times 2 to the n, right? So it's half of n times 2 to the n. Yes, you had some question? Yes, you had something?
You could say that the number of edges the degree of each vertex could also be n choose 1 because we choose.
Yeah, n choose 1 is equal to n.
Yeah.
N choose n is 1 is equal to n. Okay? Yes. No? Okay, so that's it. Now we are going to talk about one other class of graph. Again, you will hear this word again. We used it for representing function, representing relations, right? And so just now today, just we hear some more formal things about it. We representing some formal notations about bipartite graph and just some characterization, and then we move on to the major topic of trees. Okay, so a graph is bipartite. A graph is 2 things: set of vertices, set of edges. It's called a bipartite graph. A bipartite, a graph on 2 parts, right? If the vertex set can be partitioned into 2 parts such that there is no edge within a part. Okay, so look at this diagram. This graph, I have partitioned the vertex set into these circles and squares. Okay, that's just some notations. I can call it A1, A2, A3 and B1, B2, B3 or somehow. So this is the partition of the vertex set. There is no edge among the circles. There is no edge between any two circles, and there is no edge between any 2 squares, right, or boxes. Okay, all the edges, if any, are crossing from one part to another part to the other part. Okay, is this clear? Bipartite graph, so vertex set can be partitioned into 2 non-empty sets. Everything can be partitioned into V and empty set, right? That's a trivial partition. So we got some non-trivial partition, not empty, not full of all of V. Both sides have something. So if vertex set is partitioned into some subset L and some other subset R, such that L is not empty, L and R have no intersection, partition, and L union R is equal to V. So in that sense, and all the edges are going from some vertex in L to some vertex in R, right? These graphs are called bipartite graph. Okay, with a lot of applications in data science, you do a lot of this kind of work. So if you have on one side the set of actors or set of some of these performers, on the other side you have set of movies or set of some kind of productions, and the edge represent if A is a member of the cast of this movie B, right? There's just no point of having an edge between movie A, movie X to movie Y, right? Between movie X and movie Y, right? There's no point to have an edge between actor P and actor B, because an edge represent this actor or actress is a cast member of this movie, right? Acted in this movie, right? So it will not make any sense to have an edge, right? So it's a naturally bipartite graph. Okay, so if my user in online groups, there are users who are members of some Facebook communities, right? Facebook clubs or some online communities. A community is not a member of another community, right? A member is a community. A member is not a user is not a member of another user. This represent membership. Or Word and documents. This became the most important thing the last couple of years with this large language models and stuff. Words and documents. A word appears in a document or doesn't appear. How long or how frequently does it appear? Right, so this is a lot of things, the bag of words model, set of words model, the TF, IDF and those things. All of this are just, it's a graph where on one side is one vertex, one type of vertices, one part of the vertex set, and the other side is the other part of the vertex set, right? So we typically represent it with the adjacency matrix, where row represent vertices in L and columns represent vertices in R. Right, so we don't need to repeat it. Okay, and there are many other in scientific networks and many other things you can see this stuff, right? So this is one thing that you will see. One of the first thing you will see in algorithms course is a Gall-Shapley algorithm, the stable marriages theorem, which is very widely used in the US to assign to allocate residents, these MD graduates, to hospitals, right? When they apply. Every MD graduate do apply to residency, these 3.5 years training, practical training for some certain number of hospital. Every hospital selects certain number of applicants for whatever their criterion is, right? That becomes the input to what's called the stable marriages algorithm, this Gall-Shapley algorithm, which tries to match applicants to hospital, trying to match the preferences to satisfy the preferences of both parties. Okay, so that's why you see applicants in universities. I don't know if there are some universities that at some point, so the University of California system, UT system, at some point started to do this thing, but then it didn't work. They abandoned the system because just every university has very different criterion and substantially different priorities or requirements from the applicants. Okay, so we didn't mention graph coloring. Last time I uploaded the slides and stuff. You should do this thing. Graph coloring is coloring the vertices of the graph, okay, nodes of the graph, such that no two adjacent vertices get the same color. Okay, no two adjacent vertices should get the same color. It's called graph coloring. So bipartite graphs are essentially bichromatic, by definition bichromatic. You can color them with two vertices, with two colors, right? You see, just color the left part, the L part or the upper part or whatever, that one part is red, the other part is green. Can there be an edge between green and green? Can there be an edge between a green vertex and a green vertex? right? Because we said there is bipartite graph has no edges between one part, right? Between any pair in one part. And similarly, so that's why. Okay, look at this graph. Can I color vertices of this graph such that no two gets the same color? No two adjacent vertices get the same color? Can I color it?
Yes.
What will be the color? So color them with red and green or red or blue, whatever you like. Yeah, give me a coloring. Okay, green, blue. No, what is it? Red, green. So one is red, alternately coloring. 3 is red and then 5 is red, and 2, 4 and 6 are green. Is there any two adjacent vertices who got the same color? No? Okay. So C6 can be colored with two vertices. As that means C6 is bipartite, right? We can color it with two. So here is how you can look at C6. This is exactly the same C6. Look at it. Okay. It's redrawn. Now you can see a partition, right? 1, 3, 5 are in one part and 2, 4, 6 are in another part, and all the edges are only between the parts. There is no edge within a part, right? Is C5 bipartite? Can you color this with two colors? Can you color this with two colors?
No.
Why not? Can you color this with two color? So color one red. What must be blue, or what must be the color of 2? If 1 is red, what must be the color of 2? Green. So 2 is, and what must be the color of 3 then? Okay. What must be the color of 4? Green. And then the color of 5? Red. What was 1? Right? So now there will be this conflict, right? You cannot color C5 with two colors. Okay? So what is, for which n we should be able to color Cn bipartite? What property of n? What predicate? What? So if Cn is even, if n is even, then Cn we should be able to color with the two colors, right? All the even index vertices should be colored red, and all the odd index vertices should be colored blue or green, right? But when it's Cn is odd, this is the primary the primary statement of bipartite graph. The basic characterization of bipartite graph is that if a cycle, please understand this, if a cycle is on odd vertices, then you cannot color it with two colors. You need at least 3 colors, right? Actually, you need exactly 3 colors, right? Because you can just color this alternative colors, and then the last or the second last vertex you should color them with a third color blue, right? So the theorem is that when we know Cn is bipartite if n is even. If n is even, then you can color them with 2 colors. One color should go to one partition, the other color should go to the other part, right? If Cn is odd, then you cannot, if n is odd, then Cn is not two colorable, Cn is not bipartite, right? And it turns out this is the only problem with the only characterization of bipartite graphs is that a graph is bipartite if and only if it does not have a odd cycle, any odd cycle. If there is an odd cycle, the graph will become non-bipartite, and if there is if the graph is non-bipartite, there must be an odd cycle. Okay, so it's a very important characterization of this thing. One more just word that you should hear is called complete bipartite graph. Okay, complete bipartite graph, just like we saw complete graph. What is a complete graph?
Has all possible edges.
All possible edges are present. So a complete bipartite graph is a bipartite graph, let's say m vertices in one part, n vertices in another part, and all possible edges present. Okay, so here is a complete graph on 3, 3. This is denoted by kmn, where m is the number of vertices in one part and n is the number of vertices in another part. Again, I know it's a complete graph, so edge set or edges are completely described when I know how many edges are there, right? So in this case, I want to see how many edges are there in each part, right? So kmn, this is k3, 4. What's the degree of every vertex here? What's the degree of every vertices in the down? What's the degree of every vertex in the top set? 4, right? So in general, if you have kmn, what will be the degree of every vertex among the m vertices? No, every vertex among the m vertices, n, right? And every vertex among the n vertices will be m, right? They will be adjacent to all the m vertices in the other part, right? So the question is, how many edges will be there in kmn? K sub mn. What is, again, just describe the word k sub mn. What is k sub mn? No, what is kmn? What is this? Just substitute the word k sub mn. What's the dictionary meaning of this? K sub mn. What is kmn? Huh? A bipartite graph on m plus n vertices, where m are in one part and n are in the other part, right? And all possible, a complete bipartite graph, so all possible edges are present, right? So what's the degree of, so what is the total number of edges? Why m into n? Yeah, so can you do it with sum of the degrees part? Sum of the degrees way of doing it? Why not divide by 2? Where is that divided by 2 not appearing? Is 2 into m plus n? Why 2 into m plus n? M times n.
Because first m times n for the top ones, and then n times n.
Yes. So every vertex on the top set has degree n. So it will be m times n, the sum of degrees. Every vertex in the bottom part has degree m. So it will be n times m of the sum of the degrees. The total sum of the degrees will be 2 times n times m, which so that's why the number of edges will be half of that. It's n times m. Okay, mn or nm, right? And simple counting rule or counting principle, you can do this thing. Okay. So now finally we come to the main topic. Okay, this is the topic of this course. I call this topic will be this thing. Now we'll see some more proper math there. So far it was just words and definition and description and using handshaking lemma or some basic definitions. Okay, so trees. Understand this thing, drill it down into your brain, right? Or drill down to your each other's brains or whatever you do. A tree is a connected graph which has no cycle, right? So tree is a new word, that's why it's blue, it's red. Connected graph. When is a graph connected? What does it mean for a graph to be connected? Huh?
Every vertex is connected to each other.
Every vertex is connected to each other?
Every vertex has at least a degree 1.
There exists a path
Between?
any two vertices.
So every yes. A graph is connected if every pair is connected. If there is a path between every pair. A graph is connected if every vertex is connected to every other vertex, right? It has nothing to do with the degree. It has nothing to do with the degree 1 or an edge or anything, okay? A graph is connected if every vertex can reach every other vertex. If every vertex can send a message to every other vertex, right? That's a graph is connected, okay? You know what a cycle is? You know what a cycle is, right? If it's a sequence of vertices such that every successive is an edge in the first vertex in the sequence and the last vertex in the sequence is an edge. Or pictorially, you can start from one vertex, start going to other vertices through edges and come back to this vertex, okay? So if you have a graph which is connected and it has no cycle, that graph is called a tree, okay? Understand this thing, its graph is called a tree. You will see this line on almost every slide below it, and if you don't see it, you should have it in your picture. I told you, drill it down into your brain, right? It should be there on top of your head all the time. Now on, a tree is a graph which is connected, see the underlining, and which has no cycles, right? So I have underlined it, I have bolded it, I have color coded it. so that you understand. That means it's a very, very important concept, right? Just based on this line, seriously, just based on this line, and just substitute the definition of connectivity and the definition of cycle and no cycle, just every single word in this thing, we'll expand it, and all the slides will be based on this one sentence. Okay, is clear? There will be one more sentence coming there. This is a special type of it's also a very closely related concept, and everything now will be based on these two lines. Okay, which one of these 7 graphs is not a tree? Is the first one a tree? Is it connected? This V-shaped graph, is it connected? Yes. So is the first vertex connected to the second vertex? Yeah, it's adjacent. Is the first vertex connected to the third vertex? Yes, it's not adjacent, but it can reach from A to the middle and the last one, and vice versa for all pairs. You can do this, right? Is there any cycle? Can you start at one vertex without repeating, go through edges and come back to this vertex? No, right? So all these 3 are trees. Is this connected? The 4th graph, is it connected?
Yes.
Can every vertex reach every other vertex?
Yes.
Is there a cycle?
Yes.
You see this cycle here, this quadrilateral, right? It's a cycle. So this is not a tree. Okay. How about this one? This one. This is a cycle, right? This one is a connected graph, and it has no cycle. So which one are not trees? These 2 graphs. Okay, among these, which of them are trees? These are the graphs that we studied earlier. Is K4 a tree? Is K4 a tree? Why not? Where is cycle? Yeah, choose any 3 vertices, you will get a triangle, and choose the 4 vertices, you get actually the K4s, right? Many ways to find a cycle. Is C4 a tree?
No.
Why not?
There is a cycle.
It is a cycle, right? It is a cycle, so it has a cycle. Is W4 a tree? Why not?
Again, there's the outer cycle.
Yeah, it is a cycle union with the star, right? So it is a cycle, it has a cycle. P4 a cycle?
No.
Is P4 a tree?
Yeah.
P4 is always, Pn generally will be trees, all paths will be tree. How about stars? S4, is it a tree?
Yes.
Okay, so we'll just come up with a characterization that we don't have to look in the picture and see which one is a tree. Okay, so this is the second sentence I told you that will be somewhat important, and this is just there for the sake of completion. A forest is a graph which has no cycle. What's the difference between this definition and the tree definition? A forest is not required to be connected, right? And so a forest is basically, look at this. This is one component of the graph. This is another component of the graph, right? There are 2 components. Is this graph connected?
No.
Does it have cycles?
No.
So this graph is a forest, right? Is it clear? This is a forest. Now, how many components must be there in a forest? A forest which is not a tree, how many components will be there? Can it have one component?
No.
Why not?
So that would just be a tree.
Why can't the forest have one component?
It would have a cycle then.
So one component means this whole graph is connected, right? This whole connected component, and that's connected graph. Because if I say it's not connected, then it should be at least 2 components, right? There should be some disconnectivity, some unreachability between a pair, right? So there will be 2 components. But this is clear. Just understand, yes, it's a forest, if it's not a tree, must have at least 2 components. Yes.
So that graph is one graph, right?
This graph is one graph and it has 2 components. Yeah, 2 connected components. Okay, how many components? So if a forest that is not a tree must have at least more than 1 component, right? At least 2 components. Can a connected component of a forest have a cycle? If I get 1 connected component, can there be a cycle in that component? Why not?
Definition says no cycles.
Yeah, the definition says the whole graph has no cycle. So every part of it, every component of it has no cycle. right? What does it mean? A connected component is connected, right? If it's a connected component of a forest, it cannot have a cycle. What does it mean? Every connected component of a forest will be a tree. Okay? Every connected component of a forest will be a tree. So that's it. We are done with forest. We're now going to talk about it. So a forest is basically a collection of trees, right? A bunch of trees is called forest. And that's what, yes?
So could you please go to the slide where we did the classification of trees, in which we had this one. In the first one, self groups are not allowed. So how
When I began this lecture with, when we say graph, we mean simple undirected graph. Okay, yes.
we know that in simple connected graphs, self groups are not allowed.
Sorry.
In simple connected graphs, self groups are not allowed. So how do we say that in the first one there is a path from the first vertex to the first?
Yeah, this is the path, this is an empty path, right? The sequence of vertices, the first vertex is the same as last vertex, and there is an edge. So this is a trivial path, right? Can this vertex send an email to itself? Yes, it can, right? So it's an empty path. No need to go out, just right. Okay. So coming back to trees, this is as I told you, you will see this in almost every slides, space permitting. A tree is so now we're going to do some very different way. What does it mean, this definition? Okay, so we're going to come up with characterization of trees. Okay. A graph is a tree if and only if there is a unique path between any pair of vertices. Now, a graph is connected if there is a path between any pair of vertices, right? That's what we know, that's a connected graph. Graph is called a connected graph, or is called connected if there is a path between every two vertices. Otherwise, it's disconnected, right? If there is a pair for which there is no path, then it's disconnected. It's called a tree if the path between any two, if it's connected, meaning there is a path, but there is only one path between any two vertices. That's called a tree. Now see, look at this thing. Connectivity comes that there exists a path. Acyclicity, this no cycle, gives you this thing that there must be a unique path. It's clear? Understand these things. These are your ICPs or your take-home problems, and a lot of things you will see in your problem sets about this, right? Your practice problem or the exams and everything about this stuff. That these are actually the same statement as this blue statement is exactly the same thing as the statement in the theorem. Okay, in the theorem block. Okay, so it's if and only if statement. I'll need to prove two implications. If graph is a tree, then there is a unique path, and then the converse. If there is a unique path between every pair, then the graph must be a tree. Okay, so if graph is a tree, then is there a path between any pair u, v and v? G is a tree, then is there a path between if graph is a tree and you pick two vertices u and v, is there a path between u and v? Why? Because the graph is connected, right? So u and v have a path. I'm going to show that there will be a unique path, right? So if I want to show a graph is a tree, I got to say between u and v there is a path. To prove uniqueness, what will I use? What tools do I have? What additional information do I have about this graph? I got this graph, I pick two vertices u and v, and I say, okay, there is a path between them because the graph is connected. Now I want to prove something more. What must I use? Acyclicity, the fact that this graph has no cycle, right? That is I need to use. So suppose I have a graph which is a tree, and I pick two vertices u and v, and there is a path between them, right? So for the sake of contradiction, assume there are two different paths between them, right? So this is one path, this is the magenta path between u and v. Suppose there are, for the sake of contradiction, it is a tree, but still there is no unique path. There are multiple paths, right? So here is the other path, the green path, this iron path, right? Suppose there are more than one paths. They may intersect, they may not intersect, they may share an edge, they may not share an edge, but they must share at least two vertices, right? Both paths have u as an endpoint and v as the other endpoint, right? So they must intersect at those two endpoints, and they may possibly intersect it in the middle somewhere, right? They may even share some edges, right? So they may, so maybe you could, this path also started, then came back to this city, then took the same route up to a few towns, and then started to go some other way, right? Do you see a contradiction in the diagram? What is the contradiction? There must be a cycle, right? Then the graph was not a tree. That's a contradiction. You said the graph is a tree, and I found a cycle there. It's not a tree, right? So the graph is both a tree and not a tree. It's a contradiction. Okay. Now this is, you really have to go home and understand this and write it properly in a thing, right? Proof by diagram is not a thing, right? You have to write this properly. Suppose there is a path between u1 to u and v. Let's call it u, a1, a2, a3, a4, right? Where the first vertex is u, the last bk is equal to v, and then there is another path b1, b2, b3, b5, where the b1 is u and bk is l is 5, or whatever, u, v, or okay, so right, and now you see that there will be some intersection, and you should be able to write there is a cycle there, okay, to write the cycle in the formal word. The whole course began with this thing. We are teaching you a language thing that you can describe something, right? Now you should be able to describe something, this thing, okay? So the one part is clear. If the graph is a tree, then there must be a unique cycle, unique path between. But the statement is a if and only if. It's a by implication statement, right? So let's prove the other side. If there is a unique path between any u and v, then the graph must be a tree, right? If there is a unique path between any u and v, then the graph must be a tree. Okay, that's what we want to prove. So I know the graph is connected, right? I know there is a path, a unique path exists between any two. So there is a path between two vertices because the graph is connected, right? Suppose this graph is a cycle. Suppose the graph is not a tree. There is unique path, but it's not a cycle. Pick any cycle in this graph, right? Pick any cycle in this graph. This is a cycle in the graph. What do you see? Huh? What do you see in this graph? There are multiple paths, not non-unique paths between u and v. You can take from u to v the upper path, or you can go the lower route, right? And that will be another path. See this? So if the graph is has a unique path between every pair of vertices, it cannot have any cycle. It must be a tree. Okay? This clear? This was the one characterization. Trees have many characterization. Okay? Definition: a connected graph on n vertices with no cycle, okay, or sometimes called acyclic graph. We saw the directed acyclic graph earlier, right? That prerequisite chart. So an acyclic graph and a connected acyclic graph is called a tree, right? There is another characterization of the tree. So this is what you have to complete. Not now. This is your take home ICP. Complete it. Okay. A leaf in a graph is a vertex with degree 1. Okay, a leaf is just a special vertex. We call it if every vertex has some degree, could be 0, could be 1, could be n minus 1, right? Some number between 0 and n minus 1. If the degree is 1, then we call it a tree. We call it a leaf, right? The graph could be a tree, could be have a cycle, could be anything, right? We just call a vertex whose degree is 1. We call that vertex a leaf, right? The theorem is that every tree must have at least one leaf. Okay, every tree must have at least one leaf. If the graph is a tree, then it cannot happen that every vertex has degree greater than or equal to 1 or 0, not 1. Is this clear? What must we use to prove this statement? We just substitute the word tree. What is a tree? Connected graph with no cycle. Okay, so let's see. So suppose this graph, I have a graph which claims to be a tree, and that graph does not have any, that tree does not have any leaf, right? So what does it mean? So, no, what does it mean? The tree does not have a leaf. Sorry? No vertex has degree 1. So what must be the degree of every vertex? 2. Why not 0? 0 is not equal to 1. Huh? Yes. So suppose I have a tree such that every no vertex has degree 1. So then I would say, then that means every vertex has degree greater than or equal to 2. Somebody can say, why not 0? 0 is not equal to 1. You said no vertex of degree 1. You didn't say anything about no vertex has degree 0. No vertex of degree 0 is implied in it's just embedded into the word tree. It's a connected graph. That vertex must be able to reach something, right? So unless it is a 0 degree, unless it's a, yes. Yeah, okay, so unless this is an empty graph. So let's say we talk about trees, so maybe I'll correct this thing. Technically speaking, if we call this thing a tree, this one vertex with no edges, the empty graph is a tree, then this graph has no leaf, because this one vertex degree is 0, right? So it's just talking about graphs of at least two vertices, trees on at least 2 vertices, okay? Trees of order at least 2. Okay, so suppose I have a tree which doesn't have a leaf, but that means every vertex has degree greater than or equal to 2, right? So let's see if I can draw a contradiction base from this, right? I'm going to prove it this follows. So I have a graph, no leaf means there is every vertex has degree at least 2. So begin at some vertex. Please pay attention to me. Please pay attention to me. Begin at some vertex. Does this vertex have any edges incident to this? Take any vertex. Will it have any edge incident on it?
Yes.
Why?
It's a connected graph.
Because we said there is no leaf. Because we said there is no leaf. Every vertex has a degree greater than 1.
No, yeah, so greater than 1 doesn't have to do leaf. We just said every vertex has degree at least 2. So this vertex have at least 2 edges incident on it, right? On it. Is this clear? So begin that. So take any edge. Just go through any edge. Follow any edge. You start from this vertex, you follow this edge, go to some next vertex. Does this vertex have edges incident on it? The second vertex, why? Where are edges, why are edges incident to the second vertex? So I start, this vertex has at least 2 edges incident to it. Then I go to this vertex. Does this vertex have edges incident on it? Why? Because this vertex has degree greater than or equal to 2, right? So that's it. Now I'm going to say from the second vertex, go through, follow some unused edge. Unused edge. Does this vertex has an unused edge incident on it? Does this vertex has an unused edge incident on it? Huh? This vertex has edges incident on it? Yes, at least this one is incident on it. Is there any other? That must be unused, right? Yes? So take that vertex, use that, follow that vertex. Does this vertex have, what is the degree of this vertex? At least 2, right? The degree of this third vertex is at least 2. Does it have an unused vertex, unused edge? Does it have still an unused, unutilized, untraversed edge, right? Take that edge, okay? Continue doing this. Suppose you reach a vertex who has no unused edge to continue your instructions, following your instruction. My instruction is start from a vertex, go through an unused edge, from that vertex go through an unused edge to some other vertex, go through an unused edge to some other vertex, right? Continue doing this. Can I be stuck, or when will I be stuck, or what will be the situation when I am stuck? When will I be stuck? Why can't I move out? What is the instruction? Use an unused edge. Okay, go through an unused edge. When can I be stuck? So when there are no more unused edge, right? So I used only one edge for this vertex, right? Only one I used edge for this. Is it true? Can this vertex have unused edges? This vertex can claim that I have no more unused edges, right? Because the guarantee was, the requirement was degree 2, you use 2 degree for this vertex, right? But this vertex, can it say that I have no more unused edges left? What if there is an unused edge but it's going to the previous vertex? Okay, so it could be, the only reason I could get stuck if everybody is degree 2 is if I reach an already visited vertex. Okay, if I reach an already visited vertex, then maybe this graph is a finite graph, right? How long will it go? There are not infinitely many vertices, cannot just keep on going to new vertices. At some point it has to come back to the already explored vertices, right? At that time, what do I know? The graph was not a tree, right? Why do we conclude, how do we reach this conclusion that the graph has a cycle? Because you claimed that every vertex has degree at least 2. Okay, it's a tree and every vertex is, okay. Again, write this as a formal proof. Okay, yes please. Actually, the correct statement is, that's also true, every tree has at least 2 leaves, we know that. But that's not like these are not mutually exclusive. This one is still true, right? Because greater than or equal to 1 is subsumes greater than or equal to 2. Okay, a little bit more of characterization. We know what a leaf is, right? Now this is actually the main characterization of a tree. Any tree has any tree on n vertices has exactly n minus 1 edges. Okay, any tree, remember we said a path. How many vertices were there in a path? On n vertices, n minus 1, right? How many vertices were there in a cycle on n vertices? N, right? So come back. A tree has exactly n minus 1 edges, no matter how is the structure, no matter what are the degrees of vertices, just from the fact that it has at least 1 leaf, we will prove that every tree has on n vertices has exactly n minus 1 edges. Okay, there are many possible types of trees you can make from n vertices, but all of them will have exactly n minus 1 edges. This acyclicity and connectivity requirements puts a huge amount of restriction on the structure of the tree. Okay, so the proof is by induction. I want to prove what? Any tree has n vertices has exactly n minus 1 edges. Okay, the proof is by induction. The induction begins with the basis step. What is the base step? So let's say it's a tree on 2 vertices. How many edges are there? A tree on 2 vertices, how many edges? Yes, that 1 edge, right? A tree on 2 vertices has exactly 1 edge, right? And that 1 is equal to 2 minus 1, right? So we are done. Base step is true. So suppose this statement is true for any tree on n minus 1 vertices or k minus 1 vertices, right? I'm going to prove it for a tree on k vertices or n vertices, right? The next one. Okay, so let's begin with the tree on n vertices. The theorem says there must be a leaf. That's what, let's look at this leaf, right? Some tree, just one vertex, at least one vertex with degree 1, right? I take that vertex and remove it. So I remove this tree vertex, that's u. I get the graph called, let's call it t minus u. I get the graph called t minus u. Okay, how many vertices are there in t minus u? If I look at the graph, remove this vertex, how many vertices are there in t minus u? I have a graph on n vertices. I remove one vertex. How many vertices are there? Minus 1, right? Okay. So t minus u is a tree. Why is t minus u a tree? If I take a graph which is a tree, okay, I remove one vertex, will the remaining be a tree? Can the remaining have a cycle? Because removing an edge cannot create a cycle, right? Is it clear? Removing an edge cannot create a cycle. We cannot connect anything extra. But removing an edge can disconnect the graph. Removing a vertex can disconnect the graph, right? If I remove this graph, if I remove this vertex, it disconnects these two, right? Yes. So the remove is if t minus u may not be a tree, but this is not any u. This is a u whose a leaf, whose degree is 1. Removing this u will never disconnect the graph. Is it clear? Removing this u will never disconnect the graph because this u has degree 1. Suppose this is a graph u and it is a leaf, it has degree 1. Suppose when I deleted it, this vertex A now cannot reach this vertex B. Previously it could reach, there was a path, but now there isn't any path between A and B because I deleted u. What does it mean? That path was going through u, right? That u was somewhere here. That means u has degree at 2, right? The path used to go through u, meaning the path entered the vertex u and then exited the vertex u, right? So u must have degree at least 2. So if I delete a leaf from a graph, the remaining graph will still be connected and the remaining graph cannot have a cycle. Okay? So the remaining graph is a tree on n minus 1 vertices. By inductive hypothesis, any tree on n minus 1 vertices has exactly n minus 2 edges, right? So that those n minus 2 edges plus this one edge will give me in the global tree n minus 1 edges in this tree on n vertices. Okay, just using the fact that I deleted a leaf. Okay, so one final theorem that we are going to do about tree characterization is in terms of cut edges. We saw cut edges. Cut edges are those edges that are actually necessary for connectivity in the graph. Okay, very necessary for connectivity in the graph. So look at this graph. If I delete this edge E1, what happens to the graph? If I delete this edge E1, what happens? What happens to the graph? The graph gets disconnected, right? Because this is what we call a cut edge. If I remove this edge E1, the graph, if I remove the edge E2, what happens to the graph? It's not disconnected, right? The remaining graph still is connected, right? It's not very important critical edge. Okay. So here's a connected graph is called 2-edge connected if this has no cut edge, right? If no edge, no cut edge, then it's called 2-edge connected. Anyway, so an edge is not a cut edge if it is on a cycle. Okay, so let's just prove this statement. It's not a very big deal. An edge if an edge is on a cycle, can it be a cut edge? Suppose there is an edge that appears on this cycle. It's part of this cycle. Can this edge be a cut edge? If I remove this edge, can I lose connectivity? Why not? Right? So whenever, if this edge is broken, then I can always use this longer. So suppose some A was using this edge to reach some B, right? Now I can still go from A, take this longer detour and to V, and then go from V onward, go to B, right? So if an edge is on a cycle, it cannot be a cut edge, right? If an edge is on a cycle, it cannot be a cut edge. Similarly, if an edge is not a cut edge, then it must be on a cycle. Not a cut edge mean this being there, the graph is connected, this not there, still the graph is connected, meaning there are at least two paths, and they will actually, we saw the union. Okay, so a tree is a connected graph with such that every edge is a cut edge. Right? So every edge is a cut edge, every edge is critical. No edge is redundant, no edge is just there as a secondary edge. Okay, so if two vertices are connected through in T, they must be connected in G. Okay, not big deal. Just so if the graph is a tree spanning tree, then the graph must be connected, right? In the other direction, if the graph is connected, then it must have a spanning tree. I'm going to give you a constructive proof of this. Suppose the graph is connected. Suppose it is a tree. Then is there a spanning tree of the graph? Yeah, which one? The G itself, right? Take the whole graph G. Graph is a subgraph of itself, right? So, and it's a tree, it's connected, and it's a tree, so it's a spanning tree. So, suppose the graph is not a tree. It is connected, but it is not a tree. What does it mean? A graph is connected, but it's not a tree. What does it mean? It must have a cycle, at least one cycle. Find a cycle, delete any vertex you want from it. Did I disconnect the graph? Why not? We just said that an edge cannot be a cut edge if it is on a cycle. I deleted the edge from the cycle. It cannot be a cut edge. So the remaining graph must be connected. Is the graph a tree now? If it's tree, we are done. This is a spanning tree. I'm just deleting edges, not inventing edges, okay, not adding edges. So find a cycle. Look at an edge, delete any edge you want. You get still a connected graph. Continue doing this until you cannot have a cycle. You have a connected graph which doesn't have a cycle. What do we call it? A tree. And it must be a spanning tree, because it's on all vertices, right? The whole graph is connected. So this is a thing. Here's an application of this. Suppose I want to connect all these houses to some utility, right? So let's say some electric grid. I want to connect all of these houses to some newly installed grid station or a pipeline, a water supply station, right? Water pump. What will I do? What can I do? Okay, what is my goal? I want to use as little wire as possible, right? I want to optimize the cost. I want to do as little digging as I can do possibly, right? I want to use the least amount of length of pipes, right? I want to use the least amount of fiber cable or whatever I'm doing, right? Depending on the application. Is this clear? Does it make sense? As you want to connect these water supply to all the households, water supply station to all households. But once you use, because when you supply water to something, you have to lay the pipeline into the ground, right? So this involves digging, it involves then buying the pipeline and then, working on it. So you would like to do, instead of using 5 kilometers of pipeline, it will be better to use 3 kilometers, right? Total length. Make sense? What is the best way to do this thing? Very obviously think, should this network have a cycle? Why not a cycle? Remember we said tree has every edge very critical. Without any edge, removing any edge will disconnect it. You don't want to disconnectivity, right? You want a connected graph. So everybody can send a message to everyone else. It's a telephone network. Everybody should be able to call every other vertex, right? So cannot have but in this graph I want to be connected, but I don't need any redundancy, right? So I should make the graph actually a tree, right? I should not have any cycle. Okay, so what type of cycle should I use? This is one way, by the way, to do it. Just make a separate, distinct pipeline from the pumping station, from the grid station, from the network exchange to every other household, right? So, do you see the star topology? You can just make the star topology. Look at the total length of this magenta edges, right? And compare it with this. Much less, right? Now, this one is using still every person, the graph is connected, every person can call every other person, right? A telephone will be connected. So there are many possible solutions, many possible spanning trees. The best one is to use what's called the minimum spanning tree, right? So find the spanning tree whose total weight is as small as possible, right? If it's a weighted graph or lengths are disposed. These are spanning tree problems. You will do it in graph theory later, Prim's algorithm, Kruskall's algorithms, right? In your algorithm course, you will do this thing. I want to give you some other concept just very briefly, the next few slides, and then you can go home. Rooted tree, right? When you think of a tree, the first thing, a tree has roots and branches and leaves. So we used leaf, we used forest, and we used tree wood. So one word was left was branches and root, right? So now we can see this thing. A rooted tree is, you think of a tree, any tree, think of its drawing, right? Pick any vertex and raise it infinitely high. And think of every vertex as a ball. Think of every edge as a thread, as a rope between them, right? And now if you raise this this tree, this bunch of threaded balls up, what will happen? This is called a rooted tree. The vertex, the ball that I raised all the way up is called the root of the tree. The first level of threads is called the children, the second level thing, and then the third, grandchildren and great grandchildren, and so on. Okay. So look at this graph. If I lift up this D, the vertex D here, what happens? All edges, by the way, are of length. All ropes or threads are of strings are of the same length, right? They have, let's say, 1 meter length. So the first height, the first height will be D. 1 meter below that will be which vertices? Yeah, those vertices which are adjacent to D. They are called the children of D, right? Children of the root. Then who will be at height, 2 meters height? I'm doing the other way around, okay? So who would be like 2 meters below the top? They are called, they will be the neighbors of those vertices that are adjacent to the children of the root, who will be called the grandchildren. Okay, so that's the terminology. Is this clear? The same tree, if I make somebody else the root, then the structure will change, right? So different roots produce different tree, and yes?
There's arrows to near, what is that direction?
There's no arrows. Why? There's no, it's an undirected graph.
Would you have assigned direction to each away from the root?
So basically it says look at vertices from top down. Okay, so we're talking of vertices top down. Okay, so let's look at this. This is how we can see. There's no directions. The root is F is the root, the vertex F, right? The next, all the vertices, what will be leaves here? What is a leaf? What is a leaf? Vertices whose degree is 1. How would these leaves look like in a rooted, top-down picture of the tree? Huh? Sorry? They will have no children, right? No, it will be just at the last level, just like terminal thing. Don't use the word, these are just like dead end, right? You can't just go any further from them. Okay? So there are root, there are leaves, right? Anything other than that is called internal vertices, right? The other word, so this is, because now this is the direction or the hierarchical, or this what is called this, we established this hierarchy. So this A is called the parent of B, okay? G and E are called siblings because they have a common parent, right? The parent is F, right? F is called the root. Well, how do you see, how does F look like in the diagram? How would you describe F? Does F have children? Does F have children? Does F have children? Does E has children? Why? What's the difference between F and E? F has no parent, right? It's the root. It's not. We cannot say degree 0 or degree 1, right? So something. E has no children, so that's a distinguishing factor between them. So other than E, so F has no root. Is this clear? Internal vertex, leaf vertex, root vertex, children, parent, child. And you can also define grandchildren, siblings, and great-grandchildren, and so on. Okay? This is called a rooted tree. In your data structure course, you will see this a lot. Okay? Rooted tree, binary search tree, AVL tree, red-black tree, balanced binary search tree, journal binary tree, full tree, complete tree, M-ary trees, B trees in operating system. You will see B trees a lot. Okay, so a tree is called M-ary tree if every internal node has less than or equal to m children. Okay, so we restrict the number of children, that's called an M-ary tree. So what will be a binary tree? If every internal node has less than or equal to 2 trees or 2 children. Okay, so this is a binary tree. Is this a binary tree? How many children does the root have? Root has only one child, right? Root itself is a tree or is a leaf also. And but every vertex has at most 2 children, so it's a binary tree. Okay, here every vertex has how many children? Every internal node has how many children at most? At most 3, right? So this is a ternary tree. Okay, 3-ary tree. This one is also a 3-ary tree, right? A ternary tree. Okay. A rooted tree is called full M-ary tree. A rooted tree, which is the M-ary tree, is called full M-ary tree if every internal vertex has exactly m children. Okay, so in the previous one, is this a full 3-ary tree? Why not? Look at this internal node. How many children does it have? 2. How many children does this have? Look at this tree. How many children does each internal node have? Exactly 3, right? So it's called full ternary tree. The one on the left is full binary tree. Okay, everybody has to have exactly 2 children. Okay, so once you define this thing, right? This is now for your home. It's very simple thing. Yes.
So binary is for exactly 2 or less than equal to 2?
Less than or equal to 2 is binary tree. Full binary tree is exactly 2 then. Every internal nodes requiring to have. Okay. If you take any full M-ary tree which has k internal nodes, then it must have n times k plus 1 vertices. Full M-ary tree, so it must have m times k plus 1 vertices, right? Simple counting, if you know your counting thing, if you are able to do any decent question on your combinatorics lectures piece, you should be able to do this thing. Okay, I gave you a breakdown of some rule, right? Okay, count the number of vertices. Those vertices, it's a full M-ary tree. We know how many children every vertex have, and this is much more is there the proof, right? The proof is there, right? Here's one more statement that I leave as an example as the exercise for you. Go home, in every textbook you should be able to find this, right? That a full M-ary tree has how many leaves, how many internal nodes, how many leaves with certain properties, and okay, that's it.